Today we're going to start our, I guess really the schematic portion of the class. And so we are going to review the behavior of Mosfet devices, specifically current voltage characteristics, talk about what determines the threshold voltage, backgate effects, and things like that before we move on to current mirrors and then building on that to bias circuits, etc., to build our multi-stage op-amp. So the first thing that I want to talk about is the symbols that we're going to use in this class, because there may be some confusion because there's not a formal adaptation across all the different textbooks and things like that that you might see. So the ones that you're probably the most familiar with would be something like this. Where this guy is an NMOS. Here's our drain, our gate, and our source. And so while we're at it, we can define some critical parameters. So this would be VDG, sorry. This voltage would be VGS. This voltage would be VDS, and our drain current ID would have a direction down. And I want to make a note that for our NMOS transistor, our body connection, which isn't drawn, is assumed to be tied to ground. For a Pmos device, it's going to look extraordinarily similar. But I'm going to put a little circle there at the gate. So here's our gate, source, drain. So this is VSG, this is VGD, VSD, and our drain current is like so. So this is our Pmos, where we're assuming that the body terminal is tied to VDD, the highest potential in the circuit. Alrighty, so what we are going to see a lot more often than these guys are specifically ones with a body terminal that has been included. And so all that's really going to change is now we're going to have one more terminal and thus one more potential set of voltages. So here's our gate, drain, source, So NMOS, and then we also have this body connection. Still have our current ID. Here's VDG, here's VGS. Then we have this guy VBS, which is going to directly influence our threshold voltage. We'll see in a little bit. We could still define VDS as the potential difference between the drain and the source, etc. And for our Pmos, here's our body terminal. Here's the direction for our drain current. And then we have VSG, VGD, and ESB, like so. So really the only difference between the NMOS and the PMOS transistor models that we're using is that we're going to wind up having the direction of the drain current is going to change. For an NMOS, it flows from drain to source. For a PMOS, it flows from source to drain. And then all of our relative voltages are simply the negative value, because we can get those by switching the subscript notation, which is the same as multiplying it by a factor of -1. Alrighty, so now let's jump into our MOSFET characteristics. And the first thing that we're going to talk about is our threshold voltage. So let's consider a simple NMOS transistor connected to external voltages. So let's see. We have a situation like this. First thing, let's go ahead and label our different terminals here. So obviously our polysilicon region is the gate of our NMOS device. Let's, for the sake of argument, call this guy over here on the right-hand side the drain, which makes this guy the source, and this P plus connection is then our body. This is P substrate. So before we move on from here, a good question for the exam might be, why do I have to have that P plus connection to put a bias voltage on my body? Why can't I just connect a metal wire through a via directly to the substrate? I think we've talked about it a couple of times.
There isn't, you have to have the implant to make a connection, something to that effect.
You have to have the implant to avoid creating a Schottky diode, right? Or a metal semiconductor junction, which is a diode. And we don't want a one-way valve there, which is effectively all a diode is, right? So connecting to a highly conductive P+ region is effectively, you have metal, which has a lot of free charge carriers, connected to a P+ region, which has a lot of free charge carriers. So there's an easy conductive path, and then a P+ junction connected to the P substrate is a semiconductor to semiconductor junction. So it doesn't form a diode either. Anyway, that's the question that will likely get asked of you. So I just thought I'd talk about it real quick. Alrighty, so now let's talk about what happens if, so another thing, I guess I should label this voltage. We are going to work under the assumption that our source is going to remain grounded. And so I can call this guy, this voltage VGS, right? So if my source is grounded, I can tie these two together like so. And so I'm controlling, when I increase the voltage at the gate, I'm increasing the value of VGS. Alrighty, so when VGS is greater than 0, the gate and substrate form a parallel plate capacitor. And so what I mean by that, and we'll talk about it with a picture. So when VGS is greater than 0, what's going to happen? Well, positive charge is going to accumulate in the polysilicon layer. And that positive charge is going to repel all of the holes in this region right here. All right, so if all of the holes get repelled, what's going to happen is that we're going to be left with a bunch of negatively charged ions. And the total charge that's left underneath the gate is going to exactly match the total positive charge accumulated on the gate. So we have charge stored on the top in the polysilicon, a positive charge stored in the polysilicon, negative charge stored in that region between the two N+ implants, so our source and our drain. And so we see a simple parallel plate capacitor. And that'll be true as long as the source and the drain are actually at the same potential. Once we start screwing with the source and the drain voltages, we'll see a couple of other phenomenons. So let's write that down. Positive potential at the gate repels holes in the P substrate, leaving behind an ion-filled depletion region with no, really very few, free charge carriers. All right. So we're actually going to wind up having two capacitors connected in series. So we're going to have the depletion region capacitance, so formation of depletion region results in two capacitors connected in series, a gate oxide capacitance and the depletion capacitance. Alrighty. So our gate oxide capacitance, Cox prime, because it's capacitance per unit area, is simply the permittivity divided by the oxide thickness. So since our gate oxide is typically formed with silicon dioxide, that means that it has a relative permittivity of 4. So that's epsilon R. And we have 8.854 attofarads per micron, which is epsilon naught, the permittivity of free space, divided by the oxide thickness, which is typically on the order of 50 angstroms. And so this gives us a numerical value of somewhere around 6.9 femtofarads per micron squared. Now, obviously, the oxide capacitance is going to vary with all of the different processes that we've talked about because they all have slightly different oxide thicknesses. This is just the number that we're going to be using for right now, but that'll be provided for you for the specific processes. So if we're talking about a C5 process, it'll be one value. If we were talking about a TSMC 180 nanometer process, it might be a little bit different. but it's going to be on the order of probably tens of angstroms, because anything less than that, and the silicon no longer maintains its bulk characteristics. All right, so we have those two capacitances. In series. So if we further increase VGS, we'll see that minority carriers, so these are the free electrons in the p-type material, of which there aren't a whole heck of a lot, but they do exist, will be attracted towards the gate through the depletion region. Pen will work. So we'll have something that looks kind of like this. Here's our poly gate. Looks like garbage. Source. Here's our drain. Minus VGS, let's call it much greater than 0. So we're still going to have our ions here. But we're also going to see free electrons forming underneath the gate like so. And the total charge here, Q plus, is counteracted by the total negative charge on the bottom as before. So that's a combination of ions and free electrons pulled from our P substrate. So my question to you guys is, if we increase the gate voltage, why don't we see that the area of the depletion region just continues to increase?
Does it like squish the electrons?
So think about it from a physics perspective, right? Coulomb's law says that the force that the positive charge is able to exert is a function of distance, right? So there's going to be kind of a fixed distance before we're able to force holes. There's going to be a fixed distance into the semiconductor crystal that we're going to be able to force the holes away, right? So if we continue to put that positive charge there, we have to offset that charge somehow. And so we see that the negatively charged electrons There's still going to be some that are generated in this region due to electron hole pair, like thermal electron hole pair generation. And those guys are just going to get pulled up underneath the gate because they're attracted to that positive charge. We might also see some electrons pulled from the N plus regions of the source, or the N plus implants of the source and the drain as well. But we're going to generally see that the depletion width isn't going to continue to increase because there's not enough, the repulsion between the positive charges is too large to further facilitate that happening. So this process where we're pulling electrons right underneath our gate is called inversion. As the P-type region directly below the gate has become N-type, and there are degrees of its inversion. So strong inversion occurs when the channel formed by the minority carrier electrons becomes as N-type as the substrate is P-type. So it requires us to move a whole heck of a lot of electrons into that region between our N plus implants in order for us to have a current carrying path there. The voltage at which strong inversion occurs is known as the threshold voltage. And we'll call this guy V, TH, and we'll put a lowercase n because we're dealing with an N-type transistor, but the equation should be the same whether it's an NMOS or a PMOS transistor. Just the values of some of the components will be different. So we're going to have phi ms, which is the difference in the work potentials of the metal and semiconductor, plus twice phi f, the contact potential of the substrate, plus the square root of 4 times the elementary charge times the permittivity of silicon times the absolute value of the work function multiplied by the substrate doping divided by the oxide capacitance. So let's just be clear here. I've put metal and semiconductor in parentheses because we actually don't really use metal anymore. So that's really, it's the work function difference between the gate material and the substrate. So we might see that that does not look like phi. IM might be 4.1 volts for metallic aluminum, which was used for the gates and transistors for a very long time until we started using doped polysilicon due to the self-aligned gate process. 4.15 volts for N plus poly. So we can see that the change for an NMOS transistor is very small between the aluminum and the polysilicon, but for a Pmos transistor, 5.27 volts. So pretty appreciable difference in performance. For our semiconductor potentials, .15 volts plus 0.65 minus the absolute value of the work function for N-type. And 4.15 plus 0.65 plus the absolute value for P-type silicon. I don't recall off the top of my head what this 0.65, where that comes from. I'll have to look that up. Yeah, it's been a hot minute. I don't remember where that came from. But those are the equations out of multiple textbooks, so they're correct. I just don't remember where that particular bit comes from. Then we have our definition for our contact potential. And this is really just saying that it's the built-in potential for the one-sided junction. So phi f is kBt over Q, approximately 26 millivolts, times the natural log of the substrate doping concentration divided by the intrinsic concentration of the semiconductor. So this looks very, very similar to the built-in voltage of a PN junction, except that instead of having NA/ND over NI squared as the argument of our logarithmic function, we have N sub over NI. And again, that's because our junction is one-sided. Our depletion region is only having the negative ions. It's not a depletion region that has positive ions on one side and negative ions on the other. This is a one-sided junction. All right. And then our last term represents the charge stored in the depletion region. Per oxide capacitance. So using simply the good old relationship that C is equal to Q over V, well, Q over C must be equal to V then. So this is just another voltage. So that's why they're all measurements of potential, and they define our threshold voltage. Alrighty, so in practice, the native threshold voltage, which is what we've been talking about, obtained by the equation above, may not be suitable for all circuit designs. Particularly, it may actually wind up underestimating the threshold voltage or having a threshold voltage that's too small. So, like, if VTH approaches 0 for some values of n sub, right? What would that mean if our threshold voltage were 0?
That
What
would
would
mean, wouldn't that mean there's no current flowing? There's no like the depletion region there's no current flowing or something like that, right?
So if the threshold voltage is 0, so the threshold voltage is the voltage at which the channel effectively appears, right? And there's a possibility of charge being able to be carried between the drain and the source, or the source and the drain, depending on which way we've got things biased. Well, if the threshold voltage is 0, it means that that channel always exists, which means that there's really no way to ever turn our transistor off. So we could never use it as a switch, which is one of the two main functions of a transistor, right? It's either a switch or an amplifier. And that completely negates the switching operation because it could never be turned off if the charge always exists. So we can adjust it by adding implants. Opens into the channel area. So this is going to affect the amount of charge stored in our case, on the negative plate of the capacitor. So we're going to have to apply a larger voltage at our gate to overcome that. So we're forcing it to require a higher voltage in order to create inversion conditions. Okay, so that's what those implants will do. Alrighty, so threshold voltage covered. Now we're going to talk about how to mess around with it even further by discussing body effects, which is really just all about changing the potential of the body. So let's say that we have a potential at our body that's less than 0. So our source and drain are still 0. Let's have our gate voltage VGS be greater than 0, but not so much so that we cause strong inversion. And then we apply a voltage here at this terminal where VB is less than 0. So applying that positive voltage at our gate is again going to cause our depletion region to form underneath the gate. But if we apply a body voltage of less than 0, that's also going to attract holes as well. So our gate, the charge accumulated on the polysilicon gate is pushing holes away from the channel. And our P plus node, our P plus node there, if we put a negative potential on it, it's going to start drawing holes away. And so we're actually going to cause the size of the depletion region to increase. So as VB becomes more negative, holes in the substrate oh goodness, what did I just do? So this phenomenon then causes an increase in width of the depletion region, which in turn causes more charge to be stored in the depletion region. So what's going to happen to the threshold voltage? So if we look at our equation and realize that the last term is simply proportional to the charge stored, as that charge increases, we should see that the threshold voltage increases as well. Is dependent on the charge stored in the depletion region a larger gate voltage must be applied before inversion occurs. Since the charge needs to exceed the depletion charge to attract electrons. Alrighty. This phenomenon is known as the body effect or backgate effect. So with body effect present, our threshold voltage becomes VTH naught, which is the native threshold voltage equation above, plus the following factor, gamma, where gamma is the body effect coefficient, multiplied by the square root of the absolute value of 2 phi f plus BSB, the source body potential difference, minus the square root of the absolute value of 2 phi f. Gamma is equal to 2 epsilon of silicon, sorry, 2Q. Substrate doping concentration over the oxide capacitance. Oh, actually, I just noticed I made a mistake. Okay, sorry. So the mistake I made is that the oxide capacitance shouldn't be under the square root in these previous equations. So I apologize for that. All right. Okay, so we've talked about the threshold voltage. We've talked about how having a non-zero potential on the body terminal can influence the threshold voltage. Now, let's start talking about the more basic operation of things. So we've talked about how to turn this guy on and how to influence how it turns on. Now we're going to talk about its current voltage relationships. All right. So consider semiconductor bar carrying a current I. like so. If the charge density along the direction of current is QD, coulombs per meter, and the velocity of charge movement is V meters per second, then we can express our current I as simply the linear density multiplied by the velocity, right? So coulombs per meter multiplied by meters per second gives us coulombs per second, which is amperes or current. Now let's consider the same phenomenon in a transistor. I'm teaching a class. Somebody knocking on my door. Attempt to do a little bit of a 3D drawing here. So here, our body connection again. Here's our source. Here's our drain. And then here's our voltage. VG equal to VTH. So when VG is equal to VTH, we have inversion. So we have our channel, and then obviously below the channel are all those ions, but they can't move, so we're not really going to consider them too much. So since the onset of inversion occurs at VG is equal to VTH, the inversion charge density produced by the gate oxide capacitance must be proportional to the quantity VGS minus VTH. For VGS greater than or equal to VTH, any charge placed on the gate must be mirrored in the channel. Yielding a uniform charge density of QD is equal to the effective width of our transistor multiplied by the oxide capacitance. And that's the total oxide capacitance of the polysilicon region there, not the oxide capacitance per unit area, multiplied by VGS minus VTH. So effectively, as long as the source and the drain are at the same potential, if we apply a gate voltage at least equal to the threshold voltage, we'll find that we have a uniform charge density underneath the gate, where the amount of charge stored is simply the width multiplied by the oxide capacitance and then multiplied by that difference in voltage. Okay. So if we increase the drain voltage, the channel potential will vary. From 0 volts at the source to whatever our drain potential VD is. Causing a local voltage difference between the gate and the channel. Which varies from VG on the source side to VG minus VD on the drain side. From this, charge density at any point along the inversion layer can be written as QD as a function of X is W effective C ox VGS minus VX minus VTH, where Vx is the channel potential as a function of position. So if we look at this guy graphically, where we have this guy is grounded, so that's our body. Here's our source. E is equal to VTH. And finally, we have VD is less than VG for now. What we'll see is that we're going to have a linear distribution in our charge distribution in our layer, where this is L is equal to 0, goes all the way out to L effective, and let's say X. So we see that the charge distribution varies as we move across the channel. So as VV approaches VG, we should see that we have almost no charge stored, because on that side of our capacitor, the potential difference between the plates is smaller and smaller and smaller. Whereas on the source side of our capacitor, we should see that the distribution is at its largest, because the potential difference between VG and VS is also at its largest. So we get this non-uniform charge density, and we also have an electric field that's happening here, right? So if there's a potential difference between the drain and the source, there's an electric field applied in the channel. And so we should observe that the current that flows from the drain to the source is ID, our drain current, negative W effective C ox VGS minus V of X minus VTH. So that's our charge distribution multiplied by our velocity. So it's the same exact equation that we had for our bar, charge distribution multiplied by velocity, and the negative sign is coming from the fact that the charge is moving in the opposite direction as we've defined our length. channel. All righty. So let me ask you guys I guess it's a analog electronics 1 question. Is this charge transport from the drain to the source because of drift or diffusion?
If there's an E field, I believe that's drift, right?
Exactly right. Diffusion is because there's a difference in concentrations. So since our velocity, our charge movement is due to drift, we can say that V is simply equal to our electron mobility multiplied by our E field. And if we wanted to get specific with vectors, we could do that as well. We can also recognize that our electric field is simply the derivative of our voltage with respect to position. We can now express our drain current as ID is equal to W effective Cox VGS minus Vx minus VTH mu E dV by dx. And we're going to rearrange this guy, do a little bit of calculus here. Integral from 0 to x is the effective length of the channel of the drain current is equal to the integral from 0 to VDS of UN W effective Cox VGS minus Vx minus VTH dV, which gives us finally ID is equal to mu E Cox W effective over L effective VGS minus VTH times VDS minus 1/2 VDS squared for VDS less than or equal to VGS minus VTH. So this is the behavior of our transistor in the triode region, right? So if we plotted that function, we would see something like this. This is VDS, ID, and VGS minus VTH. VGS1 minus VTH. That's VGS2 minus VTH. And finally, VGS3 minus VTH. The stopping point that we have here actually winds up forming, if I drew it correctly, which I kind of screwed up a little bit, so let's pretend I did it right. There we go. Parabolic arc, where that arc is ID is equal to 1/2 mu E Cox W effective over effective times VGS minus VTH quantity squared. So, okay. From the plot, we can see that current capability of the device increases with increasing VGS minus VTH. And we're going to call this quantity VGS minus VTH from now on the overdrive voltage. So it's voltage. The voltage beyond the threshold voltage turns this guy on. All right. So if VDS is less than or equal to VGS minus VTH, the device is operating in the triode region. This name is a artifact of the behavior of old school vacuum tube transistors. When VDS is much smaller than VGS minus VTH, the drain current simplifies to ID is approximately mu E Cox. Sorry. Times VDS. So we have the drain current acting as a linear function of VDS. Applying that path from source to drain may be modeled as a resistor. It's actually a voltage controlled resistor because it's dependent on the value of the overdrive voltage. Alrighty. If our drain source voltage VDS is greater than the inversion voltage VGS minus VTH, or overdrive voltage VGS minus VTH, we can see that the charge density QD as a function of X drops to 0 or X less than L effective. So oops, that's crap. So we have VG greater than or equal to VTH. Over here, we have VD is greater than VG. Over here, grounded. Over here, grounded, body, source, gate, drain. And so what's going to happen in our channel, remember this is L effective. So if the drain potential is larger than the gate potential, then we're going to see that linear relationship that we had before, except that we're going to have pinch off, right? So in the region where VD is greater than VG, there's not going to be any negative charge stored in our inversion layer. And this length right here, if I can get my pen to draw it. So here's 0. This is the electric length of our channel. So we can rewrite our integral under these conditions. That's right. From x equals 0 to our electric length, ID dx is equal to, when our voltage is 0, VGS minus VTH, UE, Cox, W effective, VGS minus Vx minus VTH, dV becomes ID is equal to 1/2 UE Cox W effective over the electric length VGS minus VTH quantity squared for VDS greater than or equal to VGS minus VTH. And so we can see that the drain current is now independent of the drain source voltage. So is known as the saturation region, where an increase in VDS does not cause an increase in ID. Alrighty, so what that means, if we go back to our figure here, and we already kind of had it by looking at that parabolic shape, we're going to see that the current effectively flattens out. And at least that's going to be true for long channel MOSFETs. All right, I think we have time to talk about channel length modulation, and then that'll be about it. All right, so since the position along the channel where pinch off occurs is dependent on VDS the device current is not actually constant. In the saturation region. Instead, device current depends on a channel length coefficient. And a lot of textbooks use lambda, but we've been using lambda as our scale factor, so that would be too confusing. So we'll use uppercase as this. So now our drain current in the saturation region is going to be approximately 1/2 UE C ox W effective over length effective VGS minus VTH quantity squared. And now we're going to add in another term, 1 plus VDS minus VDS sat. So VDS sat is the value of VDS that first causes pinch off to occur. And so we can figure out what that is pretty easily for any particular transistor just based on its behavior. And that's going to come into play a whole lot when we do our analog design as well, because if we bias a transistor beyond, like we want to bias it in the saturation region for a couple of different reasons. One is that the current is effectively constant, but if we bias it too far into the saturation region, we're going to wind up losing headroom. So we're going to be playing around with this figure of merit VDS sat an awful lot coming up. All right, so parameter capital lambda represents the relative variation in length for a given VDS. And thus, longer channel devices have smaller lambda than shorter channel devices. So graphically, now let's call this guy ID. Let's call this guy BDS. our current's going to look something like this, right? So in this small region, and actually I should probably go down more towards our zero value, this is where our MOSFET acts as a resistor. We have triode region. Between triode and saturation is where we have BDS sat. We have very slight increase where this slope is due to channel length. Let's call it CLM. So with a very, very long channel device, the relative ratio is going to be pretty small. And so we should see that our saturation current is effectively constant. But the shorter channel that we have, the more pronounced the effects of channel length modulation will be. So in our C5 process, where we have a lambda of 300 nanometers, so effectively our smallest channel length is going to be 2 lambda. So after processing and all that kind of stuff, somewhere on the order of 500 nanometers, channel length modulation is going to be much less of an issue than if we were designing things using, say, the TSMC 180 nanometer technology, where lambda is effectively 90 nanometers, or roughly 3 times smaller. So the channel length modulation effect should be roughly 3 times larger. All right, so we're finishing up about 5 minutes early. When we resume next Tuesday, we're going to talk some more about MOSFET operation, specifically talking about sub-threshold currents. So if in weak inversion, which is obviously less carriers in the channel than strong inversion, we can still observe small amounts of current flowing between the source and the drain if we have things biased correctly. So we're going to talk about that phenomenon. We're also going to talk about the transconductance, because that's going to be a very important figure of merit when we are doing our small signal analysis of our amplifier designs, because it's usually going to be related in some way, shape, or form to the output resistance of our amplifiers. We're going to talk about what effect the body effect has on transconductance. And then we're going to go over small signal models, and then some other topics that are a little bit more advanced, like hot carriers, drain-induced barrier lowering, and things like that. Alrighty, so I'll see you guys next Tuesday. As I said previously, I'm going to try to have your test up for you guys to work on on Tuesday. Well, your test will be up for sure on Tuesday, and you'll have at least a week to work on it. So if you have any questions about stuff, feel free to shoot me an email or pipe up. And I'll make sure that all of the lecture videos and all that kind of stuff have been uploaded, and I'll finish up that tutorial as well. I think I might make you guys do the tutorial that I'm writing up as part of your test. So anyway, all right, catch you guys later.